Bismillahirrahmanirrahim. Assalamu alaikum. So, today inshallah we'll start a new chapter. The title is called Image Restoration and Blind Deconvolution. So what do you mean by restoration? Image restoration in general, it means that if I have, for example, an image and I want to enhance its quality. For example, it's an image that contains lots of noise, okay, or an image that has lots of distortion in it, like for example being out of focus and things like this. So here we'll see some techniques that are used for such type of image restoration or image enhancement. We already have seen a number of techniques of doing such thing. For example, the main technique that we have seen it was the filtering technique, right? Also, we have seen the histogram equalization in order to improve, let's say, the contrast of the image, right? So here, in this part, he's talking about certain techniques, certain specific techniques that we can use in order to restore the image. So, here in this chapter, first of all, we'll make an introduction to what's meant by image restoration. Then after that, here we'll talk about the representation of the image in the different, let's say, domains. Then after that, we will introduce something that is called deconvolution. We already know what's meant by convolution, okay? But here we will deal with something that's called deconvolution, and we will use it in order to enhance, or let's say, to restore the image and improve its quality. So for the techniques of the deconvolution that we will look at, we'll have three main techniques. We have something that's called Lucy-Richardson method, we have the Lyman method, and we have as well something that's called what? Blind method. Okay? In the first two techniques here, I am assuming that I know some information about the cause of the distortion or the cause of the degradation of the quality. While in the last method here, actually, I will assume that I know nothing about this, and I will work blindly by assuming certain values, and after that, I will use these values in my restoration techniques. And at the end here, we will have some MATLAB examples. Okay? So let's start by the introduction. So here for the introduction, we say that image enhancement. When we talk about image enhancement, we say that it is not limited to one aspect, okay? We say that it covers all aspects of improving the quality of an image for visual purpose, to make the image much more, let's say, perceivable. And this image enhancement may include, for example, noise removal, as we have seen before, okay? And contrast stretching. This means that I want to cover, or let's say all of the pixels of the image to cover all of the possible levels of intensity that I have, from the lowest to the highest, from, let's say, if I'm talking about grayscale, from the black to the white, okay? So we need to make some sort of stretching of this contrast, so this will improve the contrast of the image that I have, okay? The techniques that were used, if you remember, we have used histogram equalization, we have used some sort of filtering, and in this chapter we will see how can we make the restoration, how can we make the enhancement using the deconvolution. Okay? So so here the problem is that from where what is the source of the degradation of the image? For example, if I'm capturing, let's say, the image of a certain scene, so what are the different sources, what are the different causes that may result in a degraded quality of an image? Okay. Actually, as we have seen in, I think it was in chapter 2 or chapter 3, I don't remember, we have said that it may be, the reason may be the capturing device itself. Okay? This is one reason. It may be the environment in which we are, let's say, capturing this scene. For example, I have bad lighting of the scene. I have, for example, some difficult weather condition, like for example, I have a dusty storm, etc. Okay? So all of these things can be considered as the source of such kind of degradation. So I want to minimize its effect. I want to minimize its effect. So if we consider that these effects are errors, so we say that these errors can be contributed, as we have said, to many causes, including the hardware, and including as well to inner sources. Okay? While, for example, I am capturing the photo, my hand was shaking, let's say. Right? So in this case, I will have something which is called the emotion blurring. Right? Or it may be the blurring due to the out of focus. For example, before taking the image, the focus of the camera was not adjusted in a good way. Okay? So this can be as well another source of an error. So we say that this point is very important here. One of the most intriguing questions, one of the most difficult questions in the image processing is the problem of recovering the desired or the perfect image from a degraded version. Okay? And there is a lot of research in this direction. And actually, we cannot claim that we have reached the point in which we can retrieve the perfect image from this degraded image. Okay? Actually, what we are trying to do is to improve the quality of the image. So if you are talking about, let's say, distortion like blurring or due to the presence of noise or whatever, the measure that I will use in order to say whether this image was perfectly restored or not using such an algorithm is by computing something that which is called what? Signal to noise ratio. Okay? Signal to noise ratio. So in this case, actually, if I want to test a certain algorithm, I need to have some testing image. I need to have an original image and a degraded version of this image. And I will pass this degraded image to my algorithm and see what will be the output and compare it with the original one. Okay? Like this I can see whether, for example, my algorithm has succeeded or not. Okay? So, yes, I have a question. Any questions? So here we say that we argue that the ultimate objective of a restoration scheme is the inverse manipulation of the degraded model into the original non-degraded model. So here actually we are saying something like this. Let's look at this image, this let's say illustration here. Assume that this is my original image. Okay, this is the perfect, right? And here I have the defect function. And this defect function, it represents everything. Let's say it represents, for example, the capturing device. It may represent, for example, some, let's say, human sources of introducing errors. And then after that, after passing through this defect function, I will have here for this defect function, it has a certain function that I will call it H, which will be my kernel. Okay? Function in M and N, where M and N here are the position of the pixel, together with some other parameters. Okay? Then after that, this resulting image, which will be the result of convoluting or convolving the original image by the function that we have, okay? Some additional noise may be added to it, okay? That may come from different sources. And at the end, I will have this G, which will be the image that I have in hand, which is the degraded image. And it is the result of this function, which is F, convolved with H, plus a certain additional noise. I will call it, let's say, eta or something like this. Okay? So actually what I have in hand is this image G, and I want to get back what? The F. So how can we do this? Yes, we should go through these steps, but in the reverse direction. First of all, I need to minimize the effect of the added noise. So in this case, I need some sort of, let's say, filter. Let's say, مثلا, low-pass filtering or something like this. Then after that, I want to go from this F convolution H to F. Okay? So how can we do this?
Convolution is shift, multiply, and
yes.
sum, and then we can subtract, and then divide, and then shift.
Yes. One of the things is that we can, let's say, transfer or let's say transform my image from the spatial domain to the frequency domain. So So in this case, convolution actually will be converted into simple multiplication. Here actually I have what? I have capital F multiplied by capital H, let's call it anything, which is the Fourier transform of the H. Okay, how can I get the F from here? By dividing by the Fourier transform of this defect function. Okay? This is what the logic would say. Okay? And this is what we are trying to say here in this slide. We say that maybe argued that the ultimate objective of restoration scheme is the inverse manipulation of the degraded model. Here by the inverse manipulation, manipulations that we have said before. I want to convolve with the defect function and add the noise. So in order to retrieve the image again, I want to subtract the noise, then after that I will convolve with the inverse of the function. Okay? Right? Or let's say divide by the Fourier transform of the defect function. Yes? What is the defect function here is something like, for example, a function or a mathematical expression that describes, for example, the blurring effect. Okay? Like the point spread function, if you remember. Okay? The point spread function is that, for example, I will enter to my system a certain single white point, and in the output I will find that this point will be spread in my resulting image. Okay? As I go further from the point, the effect will decrease. But actually here I have got an out of focus effect. Okay? So here this defect function, it can be any function that may result in the distortion of my image.
So it's not as the noise, and why we did it?
Yes, here for the defect function, it's if we talk about blurring, its mathematical model is different from the noise. Here we call the noise is an additive function. So this means that it is something that is added to the original image. Okay, but in order to have the blurring effect, I need to apply this defect function on my image in a certain way, which is something which is called, let's say, the convolution that has the form of the point spread function. You see what I mean? So here actually, to represent in a mathematical way the effect of the distortion and the effect of the noise, they are somehow different. And by distortion here, I mean the blurring effect, like the motion blurring, like for example, out of focus blurring. Okay? And for the, let's say here, for this signal which is called eta, this is called an additive noise. Okay? This noise that comes from the surrounding and it will be added. Okay? Due, for example, to bad lighting of the scene that we have. Okay? I want to get, let's say, a capture of this class, but I don't want the effect of the light that comes from outside. So I will assume that the light that is coming from outside here is an additive noise. You see what I mean?
Yeah, but why we need it? And we can't just say.
Yes, in this model, actually, we need to integrate all of the, let's say, sources of errors that we have, whether it's distortion or noise. Okay? And of course, our system is not, we call this a lumped system. Lumped system means what? Means that here I will have the full effect of the defect function, and here I will have the full effect of the noise. This doesn't happen in real life. This is just a simplification of what happens. Of course, these things are happening in a distributed way. We cannot separate them from each other. But this is one of the simplest way of giving a mathematical model of what is happening here, while, for example, capturing an image and the effect of the errors on this image. Okay? Do you have any question? So here we say that we need to make some sort of inverse manipulation, okay, which is the deconvolution operation, okay, of the degraded model into the original non-degraded model. So if this task is performed based on certain statistical knowledge known beforehand. What do I mean by statistical knowledge here? If you remember the function, we have said that this function is function in the m and n, and something which is called theta, which can be considered as a parameter. Okay? Like for example, if you remember for the blurring effect, for the motion blurring, we need to specify a distance, a number of pixels, and an angle, which is the direction of the motion. So if I have some information about this values, I can make some sort of, let's say, partial information about the h function. Okay? So here we say that it's based on certain statistical knowledge known beforehand about the degradation process, medium and the noise. And the procedure in this case is called a priori restoration. Okay? So this means that I have enough information about the environment in which I'm taking, for example, these pictures, having, let's say, some, or let's say most of the information needed for the H function. So in this case, I can do what's called by the reverse manipulation. Okay? Or on the other hand, this information may not be available, okay, with a high degree. So in that case, we will apply something which is called like blind restoration or blind deconvolution. So in this case, I will assume values for the H function, and I will change the parameter of this H function and make some sort of trial and error. Okay? And each time, for example, I will assume a new value and see what will happen, as you will see with the methods that we have just mentioned. So here we say that the observed image here, if we talk about this mathematical model, is called G. And the original image that I want to restore here is called F. And this is the relationship between them. Okay? Yes?
All of this image is about convolution, convolute an image and reverse, and then reverse.
Yes, yes, yes. Let me ask you a question. Concerning the convolution, where did you study the convolution? You studied it in the signals and systems? Did you study the convolution in any other course? Yes? DSP. Okay, very good. So actually here, because the deconvolution and the convolution is the concept of, let's say, if I have a certain process, okay, and this process has an input, okay, and it has an output. So in this case, this process should have a certain function that represents the relationship between the output and the input, okay? Whether in time or whether in space. So in order to find this kind of relationship or to obtain the output, knowing the input and the function of the system, I need to do a convolution operation, okay? This operation, as we have said before, this convolution in other domains, like for example, the frequency domain or the Laplace domain or something like this would be converted in the form of multiplication. Okay? Did you study before the Laplace transform? Very good. So the Laplace actually is, we can say that the frequency domain that we are talking about is a special case of Laplace. It's in steady state. Okay? So here, when we talk about Laplace or we talk about the frequency domain, this convolution will be converted into a multiplication. So here we say that this F is the original image, G is the obtained image, and H here represents the degradation function that we have. Okay? And of course here the convolution should be done in 2 dimensions, since I have rows and columns for our images. Yes?
What's the examples of the defect function other than the time spread?
Yes, we have, for example, the motion blurring. Okay, this is one thing. We have as well the out of focus blurring. Okay, out of focus blurring is all of this actually they fall within what's called the point spread function. So the point spread function is a bit title under which we have different types of functions. Okay. So here for the time being, we are dealing with these 2 types of, let's say, distortions, which are called the out of focus, okay, and the motion blurring. And both of them, they can be generated in MATLAB using the F special function, okay. And we'll see there are some examples about it. Okay. So you will say that this blurring function actually should be considered as a defect function. As shown in the main block, is shown as a function of the pixel coordinates, as we have said before, m and n, together with some additional parameters. If I want, for example, to create an out of focus effect, I need to specify what is the radius of this out of focus. So this radius can be increased, can be decreased. This is one parameter. If I'm talking about the motion blur, as we have said before, I need to specify a distance and an angle in order to specify the direction of the motion, let's say. Okay, so this value of theta actually depends on the type of the defect functions that I'm applying here. Okay. Also here we can apply, let's say, a Gaussian function in order to make such kind of out of focus, right? For example, the Gaussian function In this case, I need to specify two things. I need to specify, let's say, mean value as well as a standard deviation value. In most of the cases, the mean value is 0, okay? And I want to make some sort of fluctuation about this 0, okay? So if I increase the standard deviation, the effect of the blurring will increase. If I decrease the standard deviation, the effect of blurring will decrease. Actually, the relationship between them is that the variance is equal to the square of the standard deviation. Okay? So in this case, the parameter that is needed by, let's say, the f special function, actually here it is the standard deviation. Okay? So here, as we have said before, h of n is also called a point spread function. And this point spread function, as we have said before, this is the general term that is used in order to represent this function. So here is talking about just the convolution in general. What do you mean by convolution? So here for the convolution, in the Fourier domain is identical to the result in the spatial domain. And in the spatial domain, we say that we'll make a convolution with each point in the image, okay? Which will be, in the Fourier domain, simply involves multiplying of the transform of this kernel by the image itself. So in this case, it will be element to element or element by element multiplication. Okay? And we have said before, if we talk about the convolution in the spatial domain and its counter, let's say, operation that appears in the Fourier space in the form of multiplication, we'll find that here in the Fourier domain, we will say about 2/3 of the operations, as we have said before. Okay? Because in the convolution, we have the shift, multiply, and add. While here in the Fourier space, we just need to multiply. Okay? So you will say that in many cases, it will be easier to construct the kernel as an image rather than as a set of numerical values. So in this case, it's better if this is the case, if it's better to create it in the frequency domain. Okay, in the Fourier domain. So let's say that sometimes the blur function can be measured directly by acquiring an image of a point. Okay? Which is something like, for example, one single point that has the white value, and all of the other points, for example, that are having black value. Right? So if I have, let's say, a camera, a physical camera, and I want to get its point spread function. Okay, so how can we do this? Theoretically, it can be done like this. Take a capture of a star, okay, a single star, and see what will be the output. Right? You know what's meant by the delta function? Okay? You know the delta function? Yes, it has the, we call it the delta Dirac function, which is the theoretical function that we know, or the ideal function that we know, is that at time 0, this is the only time at which it has a value. And this value approaches infinity. Okay? So we have something like this. Okay? So this is time 0. Any time before the 0 or after the 0, actually the value of this function is equal to 0. What is its, let's say, frequency components here? Actually, it has frequency components at all the values of the frequencies that we have. Okay? Right? So, another thing here. Let's assume that here I have, this is my f of n and n, and this is my h of n and theta. And this is my g of m and n. If f of m and n here is what we call it the delta function, or what is represented here in the form of an image of a point, okay, this is a point. Here in this case, the output g of mn will be equal to h of m and theta. Okay? So this is how it is represented here. We say that if I want to get, let's say, the function or the defect function of any process in this case, just apply to it as an input a delta function. Okay? In this case, the output here will be exactly equal to what? To the h. Why? From where did we get this? If, for example, I want to get the Fourier transform of this delta function, assume that here this magnitude is equal to 1. Okay? So if I get the Fourier transform of the delta function, like this, actually it is equal to what? It's equal to a constant value. Because actually I will have the same amplitude for all of the frequencies that I have. Right? Right. If I will convert this in the Fourier transform. Okay? So here I have, this is my f. I will call it f u and v. So I will call it h u and v. This I will call it g u and v. This is the Fourier domain, right? If f is a delta function, but this means that the input here is equal to how much? It's equal to 1. So in this case, what will be the output? It is g, so u and v will be equal to 1 multiplied by h of u and v. If you get the inverse transform, in this case you will have that small g of mn will be equal to h of mn, provided that the input here is the delta function that we have. Okay? So that's why here we have said that if I will apply this delta function, which is represented by the image of a single point, okay, the output here will be exactly equal to the defect function of the camera that I'm using to capture this. Clear? You understand the idea? So that's why you're saying that sometimes the Blair function can be measured directly by acquiring an image of a point. We call it a star in astronomical images, and this should be a single star. Okay, just one white point. Okay. So here we say that this implies that it is possible to remove a blur from an image by dividing by the transform of the blur, and this process is called deconvolution. So again, let's assume, for example, that this is my defect function. Okay? And now I have g. And I have succeeded in one way or another to get its corresponding h. Okay? So if I have g, how can I get the f? First of all, I need to convert it to the frequency domain, right? Okay? Then after that, if I succeed, divided by hu of v, this should give me what? Capital F of u and v. Then after that, I can make the inverse Fourier transform. I have a single problem, which is that for the values of h of u and v by which I am dividing. Okay? These values, when you find a large number of the values that exist here in the matrix that corresponds to h has the value of 0. If I divide anything by 0, this will give me infinity. Okay? And anything that is equal to infinity, of course, here this will result in a different, let's say, it will not reflect the original image in a good way. Okay? So we need to think about something else by which we can make this operation of deconvolution. Okay? So that's why here we say that deconvolution is typically used to remove the blur due to out of focus optics or motion, okay, from images. The second image must contain the point spread function of the blur. Here by the point spread function, I mean the h. So if I have the h and I have the g, theoretically I can compute what? The f. Okay? In some cases it is practical to acquire such an image by imaging a point. Here we have talked about this. The deconvolution is actually performed in the frequency domain. It should be done in the frequency domain by dividing the complex transform of the main image by that of the second image. Here I mean the first image of the main image here is the G. And the second image here, I mean the representation of the frequency transform of the point spread function, which is the H. Okay? So here, we say that when the degradation due to the blur is to be removed, then the process is not as simple as filtering out of the noise. Here we have said that this operation actually this is not that simple. Why? Because when I divide by 0, this will result in lots of infinity values. Okay? So, since the blurring of the image is essentially a convolution process between images and so, the principal procedure in any restoration scheme is finding out an inverse procedure. We have said this, okay? This operation that we are talking about is called what? It's called deconvolution. So in general, the resulting image G is equal to H, which is the effect function convolved with F, and this is the corresponding operation in the frequency domain. Okay? If I want to put it the other way around, with simple, let's say math, I want to get the F. So I will multiply both sides with the multiplicative inverse of H. So here I have H minus 1 multiplied by H multiplied by F will be equal to H minus 1 multiplied by G. H minus 1 multiplied by H, this will give me the identity matrix, which is 1. Okay? So I will have something like this. Okay? So this will be equivalent to this expression, which is F is equal to H minus 1. H minus 1 here is the, let's say, the inverse frequency transform of capital H minus 1 convolved with G. Right? Okay? Type. Right. What is the problem here? We say that this problem is not simple in reality. And actually, in many practical cases, it is useless or even impossible to apply it. Okay? It will only be applicable if I am sure that all of the values of H here are having reasonable non-zero values. Otherwise, actually, this operation it will not be practical. Okay? Because dividing by 0 all the time, I will have infinity. So this occurs mostly due to the reason that the point spread function is usually unknown and often it has the value of 0 in wide ranges of it. Okay? So hence H minus 1 will be infinite in this case. Okay? If I will divide by it, in this case it will result in an infinity. So here, also he's talking about this part which is multiplied by the noise. Actually I don't care about the noise. For the time being, I will not care about the noise. I will care just about the deconvolution. It is just saying that for the general term that we have put, in which G is equal to F convolved with H plus noise, okay? As a result of this division and multiplication and all of these things, I will find that the noise as well will be multiplied by H to the power minus 1. Okay? But this will not affect the signal to noise ratio because the original signal is multiplied by H to the power minus 1 and the noise as well. So their fraction, it will give me the same signal to noise ratio. Okay? But it will not affect the noise in any way. So here we say that with respect to this H, I have three situations. We have something which is called the white box problem. In this case, we know the H exactly. Okay? We have the gray box problem in which we know some information about the H, okay, partial information about the H, and the black box problem in which here we don't know anything about the H. Okay? Right. So here, if H of M and N, and this last case, actually, this is the, say that, this is the normal case that we have in the image processing, which is called the black box problem. In most of the cases, I may not have the ability, for example, after buying a certain camera, to compute its H. Okay? It needs nothing further, or let's say somehow complicated computations in order to obtain it.
Okay.
So in this case, yes.
Every camera has a different edge,
Yes, sure. Sure.
even if it's like the same brand but different version.
Yes, because actually, even for the same camera, you can change its value of edge by changing, for example, the focusing and all of these things. You see? And of course, the edge is somehow complex. Yani, this field is not simple as it seems, because the edge here actually is a combination of several things. It comes from the camera itself, part of it comes from the camera, and part of it comes from human sources, as we have said before. Maybe the camera, for example, its H is equal to 1. This means that the G is equal to F, assume something like this. But while we are taking these shots and all of these things, your hand is shaking. So in this case, the H will not be equal to 1. So here I have a certain component of H that is related to human sources. Okay? For example, the shaking hand and things like this, or the bad lighting and so on. You see what I mean? So here actually the H, it's a combination of several things together. Okay? We can identify the H of the camera. Okay? But the H that is coming from the human sources and the H that is coming from the bad weather and from other sources, it may not be easily to be modeled. Okay? And at the same time, the H, since it depends on the weather condition, it may be function in time. So in this case, the system will be nonlinear. So we don't need to go through all of these things. Okay? Just, we will say that here I want you just to understand that theoretically speaking, I can get the original image by using the deconvolution, which is by dividing the value of H. But this is not applicable in most of the cases. So what will be the solution in this case? What will be the solution in this case? Here we say that when the bearing function H of n is not accurately known, then it must be estimated before making this inverse filtering, and I will make some sort of, let's say, iterative method in order to see. For example, I have assumed that the value of H, it has a certain value. Okay? Then after that, I will apply this H in a certain expression and compute what will be the result of the F. And compare the result of the F that I have now with the previous result of the F. And so on. And I will repeat again until I have a difference that is less than a certain threshold. Okay? So it should be done in an iterative way. So we will say that since the attempt to deconvolve, which is the opposite of the convolution, the degraded image G without any prior knowledge of the cause that is producing the degradation, such a procedure is called blind deconvolution. If I don't have any information about the H, in this case we will do something which is called what? A blind deconvolution. So here, the deconvolution algorithms that are implemented in the MATLAB, actually we have 3 types. We have something which is called the Richardson method, we have the Wiener method, and the blind method. In this chapter, what I want you to do is to use this method. Okay? I will give you some background about, let's say, the theory of this method, but it is just for your own knowledge, to see how it works. Okay? But the idea of this chapter for you is to know that you have this method, and you need to use it in order to improve the image that you have. Okay? And of course here, most of these methods, they are iterative. What do I mean by iterative? This means that I will apply it once, okay? But I will not stop at this level. I can apply it again and again and again. So the method itself can be iterative, and the use of the method itself can be iterative. Okay? So the method here has, if we look at the outputs that we have, let's say, masalan, I have this original image, which is image A on the left. And the out of focus image, I have applied, let's say, an out of focus layer using the disk function, using the F special function, and it has resulted in this image B. Okay? Now, if we look at the results of applying this methods, here we have this image C is saying that this is an image that is deconvolved using the Lucy-Richardson method. Okay? And the D here is the one that is deconvolved using the Wiener method. And the E, it is deconvolved using the blind method, using a certain random initial blurring function. So here he has assumed that the h here, it has a random value. And here in the second case, he has used the same h that was used to blur the image. Okay? So the same h that I have used in order to degrade the image was used here in order to restore the original image. So here, of course, this is the part in which we have used a random, or we have chosen a random blurring function. And this is the blurring function that was originally used in order to degrade the image. As you can see, this result is relatively better than this one. Okay? You understand the idea? So actually here what we have an original image, as you can see, which is this one. This is the degraded image. I assume that I have this image now. This is the image that I want to restore. And these are the results of applying the three techniques. This is the Lucy-Richardson, and this is the Weiner, and this is the blind deconvolution in two cases. In the first case here, I'm assuming that I have a certain h that was chosen randomly. And in this case, I will use the same h that was used to degrade the original image.
So the F is not good, that
Yes?
F is not black.
Yes, so in this case I'm assuming that it is not a black box, and I want to see what will be the performance of this blind deconvolution if the h is known. So here the h is unknown and here the h is known. Okay? Fine. So this is for the out of focus layer. The same thing was repeated for the motion blur. Okay? This is the original image, this is the image with the motion blur, and here in this motion blur I think it was having a distance of 15 pixels and direction of 45 degrees. Okay? So as if the motion is in this direction. And this was the results. This is the Lucy-Richardson, and this is the Weiner, and this is the blind deconvolution in case if the h is unknown, and this is in the case if the h is known. Okay? So here as you can see, which one of them is better? Is the best, you can say. What do you think? How can I judge it? Compare with the original one, yes. I should compare with the original one if the original one is available. Okay, in order to compare between the performance of the different algorithms, I need to compare with the original one. By computing what, as we have said before? Signal to noise ratio. Exactly, signal to noise ratio. How can I compute the signal to noise ratio? So we know that the signal to noise ratio is something like this. What is the expression for the signal to noise ratio? Power of, let's say, the original. Second, by the power of noise. Right. How can I compute the power of the original image? Yes? Yes, we can get it from the frequency domain, and we can get it from the spatial domain as well. Yes, so here we can say that 10 log base 10 is summation of. Yes, here I need double summation because here I have two dimensions, right? I have, let's say, I, what's from 1 to m, and j from 1 to n, something like this. And then after that, I will assume that the name of the pixels are called x, something like this, right? So here I will have x of I, j, squared. Right? So this means that I will square all of the pixels and I will add them up. So this will give me something that is directly proportional to the power. Right? Right. Then, for the noise. بس نسيت اقول لكم ان احنا في عندنا الاوريجينال image I will call it X and the noisy image we'll call it, let's say, what? Yes. Here I have double summation. Yes. So it should be y minus x, exactly. Yj minus x. Yj whole square. Right? So here, if I give you, for example, two images and I tell you that the first image is the original image and the second one is the noisy image, and I ask you to compute the signal to noise ratio, okay? It will be very easy. Here, as you can see, if I want to do it, something like this, let's assume, for example, that I have these two matrices, X and Y. So here the signal to noise ratio, how can I compute it? How can I get this X squared using the matrix X? Yes? Right? It will be something like this. So this is the X squared. Right? X dot multiply X. So in this case I will have element by element multiplication. Right? Divided by divided by what? Divided by y minus x. Right? All to the power 2.
Summation.
Yes?
It's the summation.
Exactly. عندنا هنا جزء لسه ما عملناهوش. We need to make the summation. So how can we do this summation? How can we do the summation in MATLAB? Sum, exactly. So here, since this is two-dimensional, so I will make sum. I will have some sum here and some sum here. No, this is in the spatial domain. You can compute the signal to noise ratio in the spatial domain directly. Okay? Right? As you can compute the signal to noise ratio in the temporal domain by getting the original function as a function of time, okay, and the noisy function as well. Right? So what's missing here is what? Sum. And here we need another one here. Okay? Any question? Right. So here, in order to judge this quality of the images, we have two ways, either the subjective way or the objective way. Well, the subjective way is by just looking at it. Okay? And the objective way is by using some numerical values. I need to quantify the quality by using this signal to noise ratio. Okay? Of course, here, this signal to noise ratio, it will be better to have larger values or lower values? Larger values, of course. Larger values. Okay? Fine. Now let's look at this point. As we have said before, for this chapter, we are merely dealing with the H function. Okay? The additive noise, I will ignore it for the time being, because in the previous chapter we have seen some techniques with which we can remove the noise. Right? By either applying the filter in the spatial domain, like the averaging filter, the median filter, and so on, conservative filter, or by applying the filter in the frequency domain, by first converting or transforming the image in the frequency domain, then multiplying it with the frequency transform or the Fourier transform of the kernel of the filter, then after that I will make the inverse transform again. Okay? So in the previous chapter we have seen how can we remove the noise. So in this chapter we are just dealing with the H, the problem of the H. Okay? The problem of what we call it, the deconvolution. So here, for the Lucy-Richardson method, of course here, it doesn't deal with the additive noise, okay? It doesn't solve the problem of the additive noise. The additive noise can be solved elsewhere. Now we are dealing with the problem of H, to restore the F from the G. Okay? So here we say that the algorithm utilizes a known blurring function and iterates with it until it converges. So this means that here in Lucy Richardson, he is assuming that the point spread function is known. Okay? And he wants to iterate with it. Okay? Without applying the simple operation of dividing by H. Because dividing by H, as we have said before, it has some drawbacks. So, this is the equation that we have. I don't want you to memorize this equation. I want you just to know it. Okay? It's nice too. So here, f of k plus 1 of mn is equal to fk of mn. Multiplied by this h, this is the, we call it the defect function. Okay? And this is the image that we have. Okay? And f, this is the restored image. Okay? This expression, as you can see here, is, we call it recursive expression. Okay? Or let's say, assume that it is iterative as well. So here we say that f of k plus 1 with the hat this means an estimation. This means that I have here an estimation. So by knowing h and by knowing g, okay, I will first of all assume that I have an initial value or an estimation for the restored image. I will call it مثلا f hat. I will assume that all of the pixels are having the same value, say 1, 1, 1, 1, 1. Okay? And I will apply this expression on fk. I will call it fk, just substitute it here and there. Compute this expression, it will create an fk plus 1. Then get the difference between fk and fk plus 1. If the difference between them is very small, this means that the solution has converged to a certain value that I can use. But if still the difference between fk and fk plus 1 is big, so this means that I need to iterate again. So I will use fk plus 1, substitute it here, in order to get fk plus 2. And get the difference between fk plus 2 and fk plus 1, and so on. So I will continue making this kind of iteration until I find the difference between the fk's that is less than a certain threshold. So in this case, I can say that my algorithm has converged to this solution. You understand the idea? So here in this Lucy Richardson, he is assuming that he knows the H, okay? He knows the H. He has the H here, okay? And he has the image that he wants to use. Here in this case, this is the degraded image. This is the, we can say the distorted image. Okay? And I want to get from it the value of f.
So only f is unknown.
Yes.
F is unknown.
Yes, so this is the f that I want to get. Okay?
Everything is not except f.
Exactly. Okay? So instead of using this trivial expression by dividing the g by h, and since h, as we have said before, it may have lots of values that are equal to 0, I will use this iterative expression. You understand the idea? So we say that this algorithm targets the convergence of the following iteration. This iteration needs to converge. What do I mean by converging? As long as I am applying this, let's say, expression, I will find that the values of the successive fk's, they become near to each other. Okay? So here we say that f hat, since I have a hat, this means that this is an estimation. Okay? It's an estimation of an undegraded image, and h, this is the degradation function, and g, this is the degraded image. This is the input that I have. Okay? And of course, here this is the symbol of convolution. So we say that this method is nonlinear and the iterative nature of the algorithm. Here we can say that it is evident. Iterative, since I have the same value, I have k and k plus 1. So actually it is iterative. So the current value of k, the current value of f depends on the previous one that is computed. Okay? And this is the flow chart that we have. So here we load the image G, this is our input, initialize h and f. Here h, I'm assuming that I know h, okay? And f, I will give it, for example, a certain initial value. Let's say all of the pixels are having the same value. And then after that, I will apply. And look until this fraction approaches 1. Why especially this fraction approaches 1? You can get it from here. Yes? Yes? Exactly. And as long as this value approaches this value, this means that we have reached the correct f. Because here we know that g is the result of convolving the h with the f. So if I find that the convolving of the h with the f hat is approaching the g, well, this means that we are approaching the correct solution, right? And then after that, these are the different steps. So here we will loop n till n, so this means that this should be applied on the different pixels of the image that we have. Okay? And we will apply this expression. Here, instead of fk plus 1 and fk, it is represented like this t plus 1 and t. It means the same thing. Okay? This is not a power, this is just the iteration, the number of the iteration. Okay? So here, in the MATLAB, is it implemented in MATLAB? Yes, we have a ready function which is called deconvolution. Okay, deconvolution. Here you will provide it with the G, will provide it with the PSF function, which is the H function, and here you can provide it with the number of iterations that you want. Okay, you want to iterate it for how many times? And of course, here FR, this is the result, and this is the restored image. Do you understand the idea? Of course, here if you want to find the full information about the Richardson method and its implementation, you can look at it in the MATLAB tab. Okay? So, for today, I think this is enough for today. So what we have studied today is the following. All the time, when we are dealing with image processing, our aim is to restore the image in the sense that I want to enhance the image, right? And the enhancement of image can be done in several ways, of course. Here we can remove the noise of the image, we can improve the contrast of the image, we can, let's say, handle the distortion of the image. Okay? So to remove the noise, we can use the filtering. To improve the contrast, we can use the histogram equalization. And in order to remove the distortion, we need to use this deconvolution techniques. Okay? So for these techniques, we have introduced 3 techniques, which is Lucy-Richardson and the Weiner, let's say, method, and the blind method, right? And we have started by the Lucy-Richardson. The idea of the, what we call it, removal of the distortion is that theoretically speaking, I need to divide the G by H, but this practically is not possible. Okay? This practically is not possible. It may lead to nothing. Because most of the values in H here may have values of zeros. Okay? So the other alternative is to use this Lucy-Richardson, in which here we are assuming that the PSF function is known, and I have the G, and we will apply the iterative expression that we have. Okay? Next time, inshallah, we will see the theoretical aspect of the Weiner method as well as the blind method, and we will try to apply them on MATLAB.